Muy buenas tardes a todos, un gusto tenerlos por acá, un gusto de nuevo estar desde FISIC, la Facultad de Ingeniería, Informática y Ciencias de la Computación, pudiéndoles ofrecer un webinar más que denominamos hoy una masterclass relacionado pues a temas de embebidos, de electrónica. El día de hoy tenemos a un investigador invitado que está en Universidad Galileo durante esta semana. Su nombre es Eli Hughes. Él actualmente es el director de Wave Number. Wave Number es una empresa que existe en Estados Unidos y que ofrece resultados exitosos en las áreas de sistemas integrados, software, Internet de las cosas, audio, acústica, diseño industrial y creación de contenido. Eli, aparte de tener el puesto actual en Wave Number, también trabaja conjuntamente con la empresa de semiconductores NXP. Para NXP, él produce contenido técnico atractivo para la audiencia tecnológica que tiene la empresa NXT, pero más importante, brindando soporte a los clientes. En una vida anterior, él trabajó en un laboratorio de investigación aplicada en Penn State University. Él realizó investigaciones en las áreas de física, en las áreas de sensores, mantenimiento condicionado, robótica, vehículos submarinos y la parte de ciencia espacial. Eli en Penn State University también impartió cursos relacionados a sistemas integrados, la parte de FPGAs, teoría de circuitos y todo esto bajo el departamento de electrónica de dicha universidad. En su tiempo libre, él toca la guitarra, el teclado y además disfruta de estar realizando temas relacionados a la carpintería. El tema de hoy es, él nos ampliará más sobre una experiencia que tuvo al momento de realizar un proyecto desde cero. El proyecto tiene que ver con una empresa de bebidas. La charla para hoy se llama Crossing the Chasm with Craft Beer in Hand, The Road to Becoming a Full Stack Hardware Engineering. Esto quiere decir que él nos va a contar de todo este proceso, de cómo él se convirtió en un ingeniero de hardware, en un ingeniero que sería de full stack, que hizo todo el proceso desde cero, tanto la parte de interfaces hacia la nube, la parte web, la parte electrónica, inclusive hasta una parte relacionada al diseño y la manufactura de los sensores que utilizaron. Así que para mí es un agrado, pues ya cederle la palabra a nuestro expositor el día de hoy, Eli Hughes. Hi, Eli.
Hello, how are you?
Fine. How are you doing?
I'm doing well. I'm having a good
Great.
time.
So I will let you now be part with the audience and share your knowledge and be able so we can learn more about electronics and about all the projects that you have worked with related to this craft beer.
Okay.
Okay, so I'll let you now have control of this webinar.
All right. Well, thank you for the introduction. And, I hope it's interesting for everyone. When I give presentations, I normally like to tell stories. I mix stories with technical material, and I find it's very fun for everyone. So this story is one that kind of combines my background as an engineer, as well as a startup, that I founded several years ago to make a sensor for the craft brew industry to make beer. And it's a good story because it kind of covers everything from physics to sensors to having fun with beer brewing all the way to running a business. So you know usually I mention when I start a presentation, the goal is to really engage your interest with storytelling, but I like to bring in the human aspects of the information, people kind of turn off or tune out. So my goal here is to maybe, talk about some of the technical aspects, but at the same time, kind of give you some of the other stories of, how we built this product. And along the way is, sharing some experience of what it takes to kind of be what I call a full stack hardware engineer, where you can kind of do a little bit of everything. Um, I like to start with where I'm from because it's, I find it's important you watch someone presenting information to know, where they come from because it gives you context. So I'm a visitor here in Guatemala, and I always enjoy my time. So, I come from a, very different place. I grew up in Pennsylvania in the United States, in a very remote region where our village was 300 people. I grew up an old farm, and that's a picture of it. So I also grew up in a place where it gets very cold, and it snows and it's icy, and a little bit different than Guatemala. So when I tell my story, I introduce kind of what got me interested in electronics and computing, and my first computer was a Nintendo Entertainment System. I think we purchased our NES in 1986, so it doesn't feel like a long time ago, but it really was. But for me, I call it a computer, even though this was video games, and I really liked video games. It really was a computer because it got me interested in how a device like this could put graphics on a screen and make it engaging. And so a few years after we got the Nintendo, I was very young. In our middle school, when I was in the seventh grade, the only computers we had in our school were the Apple IIe. They were, a very popular computer in the 1980s and early 1990s. And that was it. There really wasn't else, and they weren't very advanced. But part of the course was that we learned how to program in a language called BASIC. So it's a very simple language, and you could think of it like, if you're familiar with programming, like Python. It's a very high level language. It's simple, but for me, I found it very empowering. So I use the word empowerment because I could write a simple program to make the computer do something for me. And while we were learning, most of what we learned in seventh grade, we just had to type programs as they were written in the manual. So we didn't get to make the programs up, but we typed a program someone else created. But I would spend extra time in the computer lab reading through the manual, and I noticed there were commands in BASIC to draw a line on the screen. And for me, when I would go home and play my Nintendo, I got very interested because it made it feel like I could program a video game, just like what I saw on the Nintendo. So one of the popular magazines at the time that all the kids would go to the local store to buy was Nintendo Power. So if you wanted to learn about what games were coming out and, maybe secrets and tricks to playing the game, you went to your local store to get Nintendo Power. I got very, very interested in the Apple computer just because of the ability to program graphics. And one connection that I made while reading the Nintendo Power magazine, along with the manual for the computer, was they had a common element. Inside, both the magazine and the manual was a reference to the 6502 microprocessor. So anyone who was around at the time in engineering space, the 6502 was a very popular microprocessor because it was inexpensive at the time that you could put them in home computers. And for me, what I learned and kind of figured out was because both of those devices, both the Apple IIe computer as well as the Nintendo, shared the same processor, it made sense to me that they looked different, but they were really the same thing, just doing two different tasks. And I got very interested in, almost addicted or obsessed with, learning how to program and, control that Apple IIe. The one question that I had, and, my instructor, the teacher at the time, really couldn't answer that well because they only knew a little bit about programming, was it used the same processor, the 6502, but anything I did on the Apple IIe was slow. Like I show a turtle. But the Nintendo at the time ran very fast. It could have much faster graphics, and it had colors, and it looked more exciting. And so for me, when I was young, I really wanted to know why they used the same microprocessor or chip, but why were they different? And as I was continuing to read the manual, there was this word I saw in there called assembly language. And in our class, we never learned about assembly language, but it was in the manual. And what I discovered, that if I wanted to become the powerful wizard to make that computer, the Apple IIe, run like the Nintendo, I needed to learn assembly language, because that was the only way you could make the system run fast enough to do the graphics. So I wanted to be that person made the popular video games. Now, as a side story, my mother, on the weekends, we would go to shopping. And in the United States, there's a term for a place you go to where people sell like used or old books, furniture, in leftover things in their home, and it's called a flea market. It's very inexpensive, and you never know what you're going to get when you go to a flea market. The reason you go is you walk around every week, and there's different things, often for a very inexpensive price. And as I was walking around, I saw this book, Programming the 6502, and I got very excited. And I was very young, but as soon as I saw this book, and it was a very low price, like maybe 25 cents in US dollars, I begged my mom to buy me the book. And at first she didn't want to, because she says, no, that's for college students. But I told her I need this book to be able to understand how I can be the wizard to program that computer. And for me, it was like a gift from heaven that this book showed up at this market, for such a low price that it was almost going to be thrown away. And that's what really got me very, very interested in computing, because then I learned that I could write fast programs and make interesting games. The problem was that we only had computers at school. Like when we went home, we didn't have an Apple computer. We could not afford a computer. So I would go home and read the book. I would write the programs on a piece of paper. So, I would spend all my afternoons and evenings writing the programs. So when I got to school, I could spend some time typing them in. Now, a fun thing I always show, in a lot of these presentations is the 6502 was such a popular microprocessor that showed up in a lot of different cultures. So in the 1980s, a popular movie was The Terminator. In The Terminator, one of the scenes in the movie when he first comes to like find and shoot people, he had 6502 assembly language on his heads up display. And I like to show this because it speaks to the how common the 6502 was. And a lot of people used it because it enabled people to get started with computing, at a much lower cost as compared to what you might have in a workplace or an office. Now, the problem I ran into is when I started high school, there were no computers in our high school. We only had them in middle school. So we had no computer programming classes. And, my family growing up, we couldn't afford a computer at home. So, I lost a sense of purpose that, I didn't like to go to school anymore because there was nothing interesting to me. And so as I went through high school, I was a very poor student. I failed Algebra 2 several times, chemistry, because I just didn't engage because nothing connected at the time. Now, one thing I did find that is connected, and you'll see this later in the presentation, is I got into music, both playing a keyboard and guitar, because, in the 1990s, there was a style called grunge that came out of Seattle in the United States, as well as heavy metal and rock and roll from the 1980s was still very much part of the culture. And I fell in love with music, both playing the keyboard as well as the guitar. Um, I did get through high school mostly because I decided for me to advance my life and do better, I had to do something. But I really wanted to get back into computing and into software. So I decided to try to apply to the Pennsylvania College of Technology, where they had an electronics program. In there, I found a real sense of purpose. I show this slide of climbing the mountain because once I saw they were doing electronics and robotics and they had computers, I put in so much extra time and effort because I enjoyed it. And, I went from a failing student to being an A student just because, I was at a place where I could study the things I wanted to study. Now, one thing I'm going to connect here is that in high school, when I was a poor student, I was still playing a lot of music. And for example, this Ensoniq SQ2 synthesizer in the 1990s was a very miraculous piece of technology. The sounds it could make was better than almost anything else. So I spent my college years kind of taking apart the devices that I loved in high school. And one thing I found that the Ensoniq SQ2, when I took it apart, it shared the same microprocessor as the Sega Genesis, which was a more advanced game system in the late 80s and early 90s. And you'll recognize, if you're in the gaming, Sonic the Hedgehog. It was very popular in college. But it speaks to, once again, I found two different devices in my life that were very important to me, but they used the same microprocessor, but they were very much different applications. One was for video games and one was for making music. And this continued, that when I played guitar, I would plug into amplifiers and digital effects processors. So we learned about digital processing in college. And then I found that inside of the Line 6 pod, which was a very popular guitar effects processor, was another Motorola digital signal processor. So all of those things that I loved, had microprocessors in there that enable them to, allow me to play music or create video games. And I fell in love with this combination of software and hardware and mathematics because it was connected to everything that was important to me. Now, once I graduated college, my oldest daughter was born, so I wanted to find a job right away. And I took the first job I could find, and it was for a small company named Cortec, and they made power electronics for NASA and the Department of Defense. And at the time, I just needed money. I just wanted a job to make money. And I said, I'll take this job for a few, short amount of time. And, I didn't even think I liked power electronics because it seemed boring. But, I soon gained a lot of experience in embedded systems with things connected to power electronics, such as piezoelectric actuators and, power amplifiers that were used in audio equipment. And I saw that they were all very much connected. And I was very wrong to think that I would hate this job because I didn't really know it, because I just didn't have the experience, which I tell this as like my first lesson in full stack engineering, is that when you see another discipline that you might think is boring or not as good as what you want to do, don't trivialize it. Don't think it's not important. It can actually be one of the best things that ever happened to you, or a source of growth in your own education. And for me, this turned out, this first job, even though I thought I would hate it, it connected me to the next activity in my life, where was the graduate program in acoustics at Penn State. So acoustics is the science of sound, and sound is everywhere, not only vibrations in the air or in the guitar, but in mechanical structures, in rocket ships. And so a lot of students who came to the acoustics program came from a very diverse background of mechanical engineering or electrical engineering or physics. I would have never gotten to this program had I not had that first job with all the work I was doing related to acoustics. And I mentioned for me, and I leave in the slide, that on the first day it was very difficult because I had to go back to school after I had left for several years. But, you know, it was such an important lesson to me that, you know, I was so ready to decide that I didn't like a certain topic, but it turned out that topic connected me to the rest of my career in things I would have never imagined I could do. Now, when I use this term full stack, I borrow it from, you know, the web development community, where they have this concept of a full stack developer. And really all that means is you combine, you know, web browser technologies with the web frameworks and rendering like you would see in a web browser. And then that's what they call the front end. And then that's combined with like web servers, programming, databases, along with operating systems and infrastructure they call the back end. And when they put those together, someone who can do both, you know, they call that full stack, meaning you can do both sides of the problem. Now, in electronics and software, you know, I've extended it to go, you know, much further, because in embedded systems, in electronics, we have something similar. And, you know, a lot of engineering programs start, you know, with the same types of topics like algebra and calculus, differential equations. That extends to logic as well as like geometry and spatial processing. You know, in most programs, you might do electromagnetics, field theory, chemistry. And you start building up into circuits, you know, devices, you know, power electronics. But once you stop there, you find in embedded systems, there's a lot more directions to go. You can take a path of microprocessors and networks and algorithms, but you can go a different route of doing FPGAs and simulation, or you could do digital signal processing, control theory, or you could get into printed circuit board design and manufacturing or supply chain. All of these things are part of hardware engineering. And so there are many stacks actually in like embedded systems where some people focus on one very small piece of it. I found just with my background that you can connect kind of beginning to the end, and it makes for like a very exciting career. Now, a lot of times in engineering and in these technical worlds, we consider all of the engineering aspects of what makes a full stack of skills. But there are other things that you need to learn. Human factors, communication skills. How do you write and speak clearly so people understand you? We're going to talk about what's called emotional intelligence, as well as other things that are important to becoming a very good developer, is, you know, a little bit of accounting and economics, as well as sales and marketing. Is that, you know, the next lesson I learned was that, you know, your effectiveness and how well you can do your job is limited by how well you can interact on a team of people who might have very different skill sets than you do. And all of these people are not perfect people. Everyone speaks differently. They, you know, the way they like to be addressed are differently. Everyone has a different interface. So it's very important to learn these skills because you're going to be working on a team. No one does something purely alone. That, you know, when you want to do something very important. And these are very other things that have to be part of your stack. Now, I also say the best ideas, you could have the best idea in the world, but they're of no use unless you can communicate them to other people and get other people to join you to build this, you know, this new invention or this new thing you want to do. Now, over time, I worked at the Penn State University doing research for a long time. But in 2017, I founded a different startup named T0 that we kind of united mechanical engineering, acoustic, and electronics with three different founders. And we kind of quickly learned of what full stack engineering meant, trying to run a real business. Now, that business developed a special sensor for monitoring fluids in big tanks. In the application we're going to talk about today was in beer brewing. I kind of put this word cloud that there's all these different aspects of this product that we had to cover, from acoustics to cloud and IoT and engineering and sensors. And I wanted to show you this example of this product that we put together, and we really had to have a team that could cover every different aspect of the design. Now, this is where the fun part comes in, where I'm going to talk about beer brewing. So beer brewing has several steps to be able to get that beer in your bottle. It kind of starts with grains that you grow on a farm, but you use those grains and combine them with water. And there's a very specific part of the brewing process called fermentation. Fermentation is one of the primary processes in beer brewing, where the beer gets the alcohol and some of the flavor. And it's also one of the steps in the process that takes the longest and, could be, much improved in a business process. So when we started the company, we worked on, a sensing system for the fermentation process. So that's what I'm going to focus on because it was the most important. So what fermentation means is, effectively, you start with a sugar water, and that sugar water is just made from water and different types of grain. And you may have heard the word like hops, like a beer is too hoppy. That's a grain that you would grow, and you add to the water and you boil it. But effectively, when you start fermentation, it's sugar water. The goal of fermentation is to take that sugar water and convert it to a sugar water plus alcohol. All brewed beverages, including like wine, use this process in some degree to take a sugary water, and you use yeast to make it all happen. And the way you can think of yeast, they're active, live little creatures think of them like little machines or robots that are biological, that do this conversion for us. When you ferment, a fluid, you also get other byproducts, carbon dioxide and heat. Part of the fermentation process, which makes it challenging, is you have to deal with these byproducts. And usually during fermentation, you have to cool the beer as it ferments because it heats up. Because of this, you need a very large tank to store the fluid in. And then sometimes for a typical ale, it might be 7 to 14 days that you have to ferment, that it takes the yeast to do its work. But other types of beers, like a lager, can take up a month. And so what that means to a business is that you need very large tanks, which translate to a lot of money or capital expenditure. You need a lot of materials, the grain, the water, the hops, to make large batches. And if something happens to that batch where you get what's called a fermentation failure, you can lose all that money, and not only the money, but the time you used in that tank. So the only thing you can do is try to monitor the process during fermentation. Now, the way a brewer, a technician would monitor is using what's called specific gravity. So if you remember chemistry class, a specific gravity is something you learn about in like a fundamentals of chemistry. All specific gravity is the density of fluid with respect to the density of water. So one device you use to measure specific gravity is called a hydrometer. And it's a very simple device. It's a piece of glass that has a certain weight or mass, you drop it in the fluid and it floats. And depending on where it floats to, there's numbers on that piece of glass that'll tell you its density relative to water. And so I show the equation. It's the density of beer to the density of water. But what that means is you need a sample of this beer. So you have to open the tank every once in a while to take a little bit of beer out to put it in a glass or a container to put the hydrometer in. You want as many samples as possible, but it's typically done once a day. The problem is, as soon as you open the tank, you can have contamination that can get in your beer, which can interrupt the yeast. The other problem is that it just takes a lot of time to do this. Many breweries will have many tanks, 5, 10, or 20, or even 30 tanks. So it can be a full-time job just taking beer out to take the measurement. The problem is that the results aren't consistent. The word for someone who works in a brewery, they call it a cellarman. Someone they refer to where you keep the tanks as the cellar. Well, because someone has to use their eyes to look at those numbers and where they line up to the top of the beer, different people can, look at that and read it differently. There are digital hydrometers, there were at the time, but you still have to remove it from the tank to do it, which was always a problem. So our business, we posed the question, what if you didn't have to do that? What if you could have a continuous reading all the time? How would that help your business process? Well, Miller Coors, which is one of the largest beer brewers in the world, did a study with Emerson Controls, and they found that on average, beer sat in these tanks for 40 to 50 hours too long, which over a year, that was 400,000 what they call barrels of beer that was just lost in productivity. They use a weird unit called a barrel of beer. It's not a metric unit, but it's very common in the industry. But it turns out it's a lot of beer in that you could have been brewing, but you lost in productivity. Now, the way we approached the problem is that we were experts in acoustics. So I had a background in electronics and electrical engineering, but a graduate degree in the science of sound, as did my colleagues who had backgrounds in mechanical engineering, but graduate degrees in acoustics. So sound speed, meaning how fast does sound waves move through a fluid, it's something that we all know that happens, right? It's the reason we can hear each other, that we know sound waves travel through air. It's also the reason that the ocean is very noisy. That's whales and dolphins communicate. We have sonar to do ranging underneath water. We have medical imaging that uses it. So the physics of how sound waves moves through a fluid is very well understood. The equation is given like this, where c, the velocity, is related to some other parameters that you find in chemistry, such as the adiabatic constant, the molecular mass, or temperature. But another way that you look at this is that, I kind of hide some of those variables, is that the sound speed is related to temperature. Now, you can rearrange those terms into other terms that we call bulk modulus, which is kind of how stiff, or you almost treat the fluid as like a spring that you can compress, and that's called bulk modulus. Then the other term is density, that we know how dense that fluid is. What the takeaway from this, the result, is that if you can measure sound velocity c in temperature, you can work back to bulk modulus in density of the fluid. Specific gravity is a density term in beer, and that's something that the beer brewers were already using. So we were experts at sound waves, so we decided to build a special sensor we called the sonic density sensor. In this image, you can see kind of a rendering. On the left side in black is the fluid. That would be where the beer's at. On the right side is kind of the outside of the tank, in a fitting. And so this sensor, as you see it spinning all the way on the right, is just a solid piece of stainless steel. And that's important because a lot of regulations when you make beverages, things have to be made out of a specific material as to not contaminate it. So we use the same steel that the tanks were made out of, so it was very safe. And because we use sound waves through this steel, we didn't need any other material touching the beer. The other thing it made, it was very easy to install. So we designed it so it fit into common openings that were on the tanks already for other sensors. So a lot of the engineering was around building this sensor so it was very easy for the brewers to put in the tank to get a reading. The other important part, we had to design it that it was easy to clean because all food production is subject to certain regulations. They have to clean the tanks and anything that touches the beer in between, different batches. Now, the way our sensor worked was actually pretty simple. So this is a cartoon diagram where on the left, we had a transducer inside of our stainless steel casing that would launch a sound wave. And you can see the sound wave traveling back and forth. Well, on the right side was just a reflector. The sound wave would hit this other side of the sensor and reflect back. And so all our circuit would do is generate the sound wave and then listen for a response. We would make a precision time measurement to figure out how long did it take for the sound wave to go through the fluid, hit the reflector, and return. Now, because when we designed this probe, the distance between where we launched or created this sound wave and the reflector, it was fixed. It was known when we built this, the probe. If we can measure that time, we can come up with sound velocity. And so how good our product would come down to how well we can measure time. Now, the speed of sound in a fluid is very fast. It's much faster than in air. And for our probe or our sensor, that time was about 50 microseconds. Now, 50 microseconds or millionths of a second in electronics actually isn't hard to measure, but the challenge wasn't the 50 microseconds, is that as the beer is fermenting and the fluid property change, that 50 microseconds changes in a very small amount. So what we were actually measuring was the change in that time. Like it would go from 50 microseconds to 50.001 microseconds. And we call that a time of flight, how long it takes for that sound wave to move. Now, how small was that change? Well, we had to be able to measure down to 60 picoseconds of timing difference. So I always show this picture of how small that is. That is a very small number in measuring a time difference, but that's what we had to do because the timing differences due to the fluid changing as the beer was brewing were very, very small. Now, the other part of the physics is that sound speed, as I showed in the equation previously, is highly dependent on temperature. And so we had to be able to measure temperature to a very, very small amount. So our sensor had a precision down to 0.02 C. The other thing we learned as we were doing this is that it became difficult because as the beer was brewing, the CO2 or carbon dioxide formed little bubbles that got in the path of our sound wave. And so I have another little animation that kind of shows what happens as the sound wave would hit these bubbles. It would scatter. It would move in different directions, which would cause noise. And we originally thought this was a serious problem until we realized that we now had an independent measure of how active the yeast were, because the more bubbles we had, the more active the yeast cultures were. And so with some digital signal processing, we could actually have two variables from our probe. We had a rate of fermentation of how active the yeast were, but we could also measure the specific gravity. So we had two curves to give to the brewers to tell them what was going on. Now, what we ended up doing was create an entire IoT system. So the brewers, they could install this sensor in 2 minutes is all it took to put it in their tank. But then they could open up their phones and see a dashboard that would give a representation of how much longer we estimated it would take to complete the brew. And so they could open up their phones or their web browser and have an application to see what was in every tank, and then get real-time data. Now, to build this product, to be effective at building this product, we had to start with fundamental math and physics. Equations for acoustics, we had to understand the chemistry. We had to understand things about acoustics. Once we understood that, we actually had to make the sensor, meaning we had to generate sound waves, and we had to measure temperature to a very precise amount. So that was the next level in the stack of information of learning about piezoelectric ceramics. After that, we have to build circuitry to read the sensors and do all the processing. So all the things you might be learning out at Galileo in terms of, electronics and timing and microprocessors. After that, oops, I have to go backwards. Our embedded device had to have software in it. We had to have C in a real-time operating system, but we also had to connect to the cloud with MQTT, and we used the cellular networks. We had to bring all these pieces together inside of our sensor. Once we measured, we had to get the data to the cloud. Well, once it's in the cloud, we have to do something with that. The brewers aren't programmers. They won't know what to do with that data. So we had to bring in all the cloud computing elements, such as, deploying on Microsoft Azure for the servers. We used Linux. We used Laravel and PHP. Our web application was done in React. We had to bring in a database and use Python. So all of these things build up in this stack to make that product. To be able to show that icon or that graphic on the web application to indicate to the technicians what's going on in the tank. And along the way, part of this, is the team building. We need to have partnerships with like NXP, who makes the chip, or Nordic Semiconductor, SolidWorks, who we use to do the 3D modeling. All of these pieces have to get put together to make a complete product. This is really the essence of the technical side of, being this full stack engineer, of being able to see this entire vision to work on a team. Now, the question you might ask is, that's very complicated. It takes a long time to learn these things, and we had to have several people involved to put it together. I was in charge of the entire system of putting this picture together. You might ask the question is, how do you learn all this? And, there's a saying that is popular called, well, how do you eat an elephant? An elephant is so large, you can't imagine eating an entire elephant. Well, it's one bite at a time. You don't eat the whole elephant at a time. You take very small bites. In all hardware engineering is incremental. You don't end up with the final product right away. We went through many variations of the same sensor design, and we had as you can see in the picture, like 15 different prototypes of size and shape. The electronics, these are real pictures. I put every piece of electronics we use from initial development through our final product. We went through a lot of prototyping to get to the end state, to get to our final product. So it wasn't overnight. We had to take very small steps along the way. And so, every product is going to have these technical problems you face, but some of the challenges we had were actually bigger. And this is when I talk about full stack engineering. The other piece of this is emotional, is that some of the biggest challenges you have won't be the technical. It's battling yourself and your own self-doubt. It's that you're going to run into problems and challenges that's going to make you feel like you're inadequate or you're not good enough. But very important, you have to put yourself in a position where you almost feel like what you're trying to do is just out of reach. You just can't quite get there, because that's where you grow. If everything you're doing is easy, you're not growing and learning new things. But it's really important that you have to be able to communicate your thoughts, your ideas, and interact with other people who know things that you don't know. And how far you can go in the types of projects you can work on is really controlled by your ability to communicate these thoughts and emotions, because the problems you run into aren't technical. They might be something else. The other message I have is you don't necessarily have to start with a complicated project. Simple things executed very well are always better than complicated projects executed poorly. But you do enough of the simple projects, you build confidence and you learn how to build teams that you can, execute projects that are much more complicated. I use this word emotional intelligence, and a lot of engineers are afraid to approach this subject because they feel it's too, it's something they shouldn't have to worry about. But it's very important, because it's just this capacity to be aware of your own emotions, and how to control yourself and handle interpersonal relationships. So you have good judgment and you're empathetic of how other people are feeling, because you have to work on a team, right? And people can be much different than you, but they might know something you don't. And the way I explain it is, if you're learning about circuits in software, well, you can't ignore the fundamentals of those circuits and software and expect success. Well, engineers, we have to understand our own biochemistry and our own psychology to be successful as well. We have to understand our own circuitry. It's very important. In one thing that shows up a lot in engineering, electronics, in software engineering, I see this all the time. It's called the imposter syndrome, and you can search this on Google. It's very common that almost all people in a technical field face this, and it's an anxiety and doubt that you don't feel like you're good enough. And when you look at what other people are doing, you think that they're somehow better, in that they studied hard, and that somehow your accomplishments were just the result of luck. But other people's accomplishments were because they were better than you. And well, it turns out that everyone thinks this, but because everyone's thinking, it's not true. It's that we all think that other people know more than we do, and we doubt ourselves and our abilities. And we ask questions like, am I doing enough? If I show my work, is it good enough? Am I the best person to be doing this? And the message I wanted to give to you is, everyone feels like this, no matter how successful they are. We all spend a lot of time in our head thinking, I'm not good enough and I can't accomplish the task. But it's not just you, it's everyone. And once you realize this, be confident. And, there's this famous saying that, and this stuck with me. And I remember hearing about this when I was very young, that when you interact with other people, most people will forget the things you say. Most people will actually forget things that you do. But everyone remembers how you make them feel. It's almost universally true. Though people will, if you say something wrong and you offend someone, most of the time they forget it. Or if you make a mistake, people will forget that. But if you make them feel bad, they will always remember that. And so, for me, my path was influenced by mentors and teachers who made me feel like I was empowered to do these things. And so that drove, a lot of my desire to stay with engineering to build new things, because I had teachers who made me feel like I could do it, even if I felt like I couldn't. And, so when I talk about crossing the chasm or, climbing the mountain, it all started with connections where in each column, or each row, I was able to connect things in my life that were important to me. And it started with video games, then it turned into like music, that those things were connected to this technology that, I could be building very interesting sensors and hardware, or, making new things if I got a grasp of this technology. And, when I teach other people, I tell them, find things that are in your life that are important to you. It may not be music or video games. It might be automobiles or working with wood or, helping people in some way. And if you have a passion for those things, you can use technology to, improve, make a new product or help someone else's life, or, make a business work better. But it really starts with things that you love, and want to work with. And so the other thing I mentioned, is getting to this point where you feel like you're a full stack, is that understand that all knowledge is an integral of like effort over time. You have to be patient. None of it happens overnight or instantaneously. It's a continuous process. And it doesn't stop when you leave Galileo or leave the university. That's just the start. It's just a slow process of learning new things and working with new people. The other thing I value personally, and I try to teach, is that, humans are different, that, we have the ability to retain information between generations of offspring, or our children. That's very important. And so one of the most valuable things we can do is teach what we know. If we know something, it doesn't have to be, a very, complicated thing or piece of knowledge, but it's important that if you know someone, you teach it to someone else, because that's what makes us different than, all the other animals on this planet. Is, I tell people it's very important that always be in this mode of being a student and a teacher, that if you know something that someone else doesn't, just freely give that knowledge, because, we all benefit from it. So, that's all I had to say today, and just wanted to kind of tell you my story and the story of this product. When I formed the startup, it was very fun to build. The picture on the screen is a robot. We actually had a cartoon character we called Brewbot, and he was kind of a fun cartoon character that was at the brewery, and we made videos with Brewbot, and we actually put him on all electronics. So he's waving goodbye to all of us. And, I just want to say thank you very much for taking the time to listen. And I hope you, found value in what I had to say. So.
So, Eli, thank you. Thank you for your time.
Oscar.
It was really nice hearing all about the full stack, how to become a full stack engineering and all the work. It was really nice.
Yeah, thank you. Thank you very much.
So here, people will start writing a couple of questions, but while that, I got from a friend a couple of questions that I think we could manage before we could start with the audience. So one of them would be, what was the most difficult area or module developed in the project from your perspective?
Here is what was probably the most difficult, and it wasn't purely technical. It's that when we started, we would visit breweries to get an idea of what their problems were, to figure out what could we make for them that would help their life. And that would kind of tell us the same thing, but in a different way. And so we had to make early versions of the sensors to present the data. And it wasn't actually making the sensor, it was figuring out what measurements and how would we present it in a way that was very useful to them. And so, believe it or not, it wasn't the really difficult circuit engineering that was hard. It was figuring out what was valuable to this customer and how would we present this data. The second part of that, which was very challenging, was building one or two sensors. It was challenging, but we got to that very quickly. We had to build hundreds exactly the same way and make this precision device. We spent about 2 years trying to get so we can make this with another manufacturer. So every sensor we built was exactly the same. And, even if you listen to like Elon Musk of Tesla, he says the same thing. Making one car is actually pretty easy. Making 100,000 cars is very difficult to make them the same way. So I would say that on the technical side was probably the most difficult part.
Okay. Related to that part of the problem, Pedro Gonzalez is asking, you mentioned hardware development is an incremental process. How or when do you decide you've achieved a final product?
That's a very good question. You achieve the final product when the customer gives you money. So and I say that kind of because a lot of products, and this is a secret that most people don't know, is that many of the products you buy, if you're to take them apart, you'll find mistakes on the circuit boards, or they'll put like little patch wires. A lot of hardware still might have bugs in it, but it was good enough to sell. But a good way to answer that is once you understand what the customer needs and it does what they want, you're always battling. As an engineer, you want to add more to it and you want to make it better. Well, when your customer says this is good enough, that's the time to stop. But I would say the other way to know is that when you can go and get someone else, or you engage a manufacturer to build, that you can reliably build a lot of them without any bugs, and they all come off the assembly line the same way, that's when you're ready. But it's a difficult thing to judge, because you have to determine when does it have enough features, and then when is it good enough to produce. And the features part is even more challenging, because as engineers, we want to add new things, but a lot of times your customer might be happy with, the first version. So, that's probably the best answer I can give, because it's not always the same. It depends on your customer, but it's very important that you can replicate the hardware you build. So that's kind of the point when you decide it's done.
How and what will be your tips to become this full stack engineering, hardware engineering?
So, and I'm going to say this almost as a joke, but it's somewhat serious, that for me, I'm always building something, and sometimes the things I'm building don't turn out to be anything. They'll just an experiment I try, because I start with projects that I'm interested. I'll try to build it to, achieve a result. But halfway through, I realize, oh, maybe it didn't work the same way. I don't get discouraged. I just do another project. So sometimes the best way is, you can learn things like at the university, or, in a textbook, or go online, but it's very important that you're always experimenting and trying to build things over and over again. And it speaks to that incremental nature that, you don't have to be perfect with any one thing, but you just have to keep trying over and over. And so even the reason I'm here this past week at Galileo to work on the Bunny Vision project came from, me riding my bicycle and wanted to put AI technology, and we're going to try different things over and over again. And over time, as you build more and more things, you gain more skills. And then as you gain those skills, you have the ability to do much more difficult things. But the one point I did mention in there that is important is when you start new projects, is if it feels really easy, it means you're not challenging yourself. You almost want to pick some things where you don't quite understand if you can make it work. but you're going to work hard to learn some new things that you're right on the edge, like you're going to fall, off the cliff or off the mountain, but it's where it's just out of reach. And that's like, it's very uncomfortable to be there, but that's the part where you're learning and you can, improve what's in your stack.
And how do you finance that trip, that travel while you are learning and before you get a product?
So here's another secret I'm going to tell you. This is the secret that it's not even a secret, but it's treated like a secret, is that and I can't remember the name of the famous person who gave this speech, but it was at a graduation at a famous university like Stanford or MIT, where the person said, when I got my bachelor's degree, I thought I knew everything I needed to know, right? When I got my master's degree, I realized I didn't know anything. And then when I got my PhD, I realized I don't know anything, and neither does anyone else. So I say that as a joke, that the way I finance it is, or build these things, is that sometimes I get work on projects to accomplish a task, and many times a customer doesn't always care how you do it, just that you get it done. So what I'll do is, while I'm trying to accomplish that task or design a circuit, I'll pick things out of that maybe are for my project, that I say, well, maybe I can use this little piece or this little circuit in a different project, or I'll choose that method of doing it where, and this is the funny part, I don't even know if I can make it work yet, but I tell them I'm going to make it work. And there's a word for that actually that we use. It's called taking ownership, meaning you take ownership of the outcome of the project, that when you say you're going to do it, you're going to do it, and you're going to figure out, even if you make mistakes along the way, like if I choose a certain part to make it work because I thought it was the right way, it's my responsibility, if it doesn't work, to figure it out. And so a lot of projects for me, and even this project, I didn't know that I was going to be able to complete it when I started. And that's the secret, is that when you see, even very popular products from Google or Amazon, when they start those projects, they don't actually know that it's going to work. They just know they want to start, and, they take ownership over that process, that they're going to make it work. So, so that's the trick, is sometimes you just say, I will make it work and I'll figure out how. And then it doesn't mean you know how, it just means you're going to put all your effort into it. And, sometimes you fail, and that's okay. It's more about that, if you do fail, you pick yourself up and you try again. And at the beginning, don't take big steps, just take little ones. So that way, if you make a mistake, it doesn't ruin the whole project. You just might spend an extra day, but over time, you gain more confidence, and you can make, take bigger steps and take bigger risks.
Here, Ali asks, how old were you when you bought that 6502 book? And do you think it was a good age to start? Did you understand it?
Well, I think, so I was very young when I was going through all my grades in school. I started about a year early, not because I was smart, but because I moved from one home to another, and there was some confusion with the school early on, and they started me in the wrong grade too early. So I was about a year and a half younger than everyone. So I think when I got that book, I just remember I would have been 10 years old when I got that. And that book was well beyond what I could understand. But when I looked at that book and I looked at maybe some of the other books that were easier, it was kind of being at that edge of what I could possibly know, but I would keep reading it and try things until, it's like I'm here learning Spanish. I can't speak Spanish, but I hear the words, I feel uncomfortable, I try the words, then someone gives me feedback. It was very much the same with that book, that at the beginning I couldn't understand anything, but then I just kept reading and trying to make experiments until I could understand everything in that book. And it did take a long time, but you know, that was practicing that skill of trying for something that is beyond what you can do, but you just stay with it until you get the result you want.
And the last question will be, so the world is every day with more IoT, more automation, robotics, and well, COVID had a problem. We had a problem with the semiconductor industry. So, what's your vision about this industry? Would it be continue always coming from Asia? Will there be some changes, and now we will have more local suppliers in America? And do we need more engineers related to embedded electronics?
I think we need a lot more engineers because embedded electronics, there's always going to be a need for people who make the semiconductors, but there's a lot more need for people who can take those and build the applications to solve problems. Like all of these things, sometimes we do it because it's fun, but we're always trying to solve a problem, maybe in healthcare or for a business. So, chips are going to keep getting made, lots more, and it's going to keep pushing into embedded, where the same microprocessor will get smaller and cheaper, so we can add them to new things. The problem of the supply chain is a big one. Unfortunately, my personal opinion is right now it's very much concentrated in Taiwan and Korea, and it's a problem because if something, well, even if it's not like purposeful, of an earthquake or a typhoon in Taiwan wipes it out, like it will shut the world down, right? So my hope is that we can distribute and bring semiconductor manufacturing to more places, as well as having more people that knows how to use them all over the planet. And I do see a need in embedded that it's only going to get more need for people who can do these embedded projects, because the chips that used to be were only in a big computer, we can now put in very small things because they're very inexpensive to make. And it's only going to go more in that direction. And there's going to be more need for people who understand how to program them, and when I teach students that we see computers and phones as the primary users of chips, it's not. It's like the car you drive, your motorcycle, your coffee maker, your refrigerator, everything that's around you has a little microcontroller in it. Someone has to write the code. Someone has to make the circuit board. Someone has to design those things. Someone has to figure out how to build them and manufacture them. And I only see both, in those regions, but you do, the manufacture of the actual semiconductor is a big problem. And, my hope is that we can get more places building even the same parts, so we're not quite as sensitive to, one place, getting shut down.
Sir,
Yes, sir.
between hardware and hardware development and software development, which is harder, and which one takes more amount of your day?
Oh, wow, that's not a quick answer. It depends on the day. So sometimes I'll say hardware can be more difficult because the decisions you make, or I'll say the mistakes you make, you might not feel for months down the road. And it takes them, because you just can't recompile your code. I'll give you an example of, if I have a circuit board and I build one and it works, and then I place an order at a manufacturer for 1,000 and they make a mistake, it might take 8 weeks before I get all those circuit boards. And this actually happened on this project where we got 1,000 circuit boards where half of them were damaged. We didn't know till 8 weeks till the order came in. Then it took us another 4 weeks to figure out why it happened. We just couldn't recompile our code. So that's very difficult with hardware. With software, the challenges are just other things. It's software gets very complex. While you can recompile your code, building it in such a way that keeps it simple can be very challenging. But like I generally think hardware is a little bit more difficult just because of the impact of a problem. You won't know it's a problem till much further in the future. So the solutions to those things can be very difficult and often requiring other skills, other than technical to solve them. But they each have their own challenges. So I don't want to like say one is worse than the other. They're just different. I just find the hardware can be a little bit more challenging if you're not experienced with it because you don't know right away that there's a bug. The bug's coming from the manufacturer and you don't have any control over it. So,
Exactly.
that's a particular challenge.
Well, thank you for your time, Eli. It was really nice. It was really nice learning about all the project, about your experience. Thank you for sharing it. Eduardo sends you greetings. He says, "Great talk, Eli. It was good to see you. Thanks for sharing your story, my friend." And so he was hearing also. So
yeah, I miss Eduardo very much.
yeah. So hopefully we will continue this kind of projects relationship with Web Number and Universidad Galileo, and hopefully we can have more webinars. For everybody, have a good night. Para todos, feliz noche, and thank you, Ile.